So hi everyone, welcome to this last lecture of this course on the statistical mechanics of disordered systems. So today I would like to start by a small digression about, so I want to make some comments about the space of probability measures and how we move in this space. So yeah, let me make a few comments about this. So I'm going to denote P of, okay, so R plus is the, okay, or P of R. So this is the space of probability measures on R plus. It so happens that the measures we care about are all with support on R plus, but what I'm going to say is equally valid for measures on R. So yeah, what I want to discuss is that, it's how do we move in this space? And I claim that there are two ways to move in this space, at least two natural ways to move in this space between two probability measures. And perhaps it's easiest to illustrate this on an example. So let's say that I'm trying to move between two Dirac masses, one which is here and one which is here. And so maybe this is the measure mu, this is the measure nu. So one easy way to move in a straight line between the two measures is to write 1 minus t. So the function for t between 0 and 1, the function 1 minus t mu plus t nu. Okay, and this leads to the intermediate picture, which is with two smaller Diracs. Okay, and then at the end of the trajectory, we end up here. But there is another way to think about moving between this Dirac and this other Dirac, which is to just slide the Dirac along the way. And this one we could think of as being more transport type derivative. So you should think that this is, the original point is here and the finite point is here, and we end up here. Okay, so we're just sliding this guy is traveling in this direction. And yes, so I want to clarify how to talk about this this second way of moving around. And so yeah, in general, if I have two measures, mu and nu, in the space of probability measures, I can first identify the optimal transport between the two measures, and this is a coupling between the measures mu and nu, which I can denote. So let's say I'm going to define it later on, but just in general, even if we were not on R plus, so I could define a notion of cost and then try to optimize this cost and find two random variables, one distributed like mu, the other distributed like nu, such that some notion of cost between these two things is minimized. This would be a coupling between the two variables. And then I claim that what we do when we make this movement on the left, the one that is here, is that this intermediate thing is the law of 1 minus t x mu plus t x nu. Okay, and this is a way to define this alternative way to move in the space of probability measures. And so I have not yet defined what is this optimal coupling, but in 1D, it's actually easy to define it. It's just the monotone coupling between the two variables. What does that mean? So you probably know that if I want to simulate a random variable with law mu on a computer, then a good way to do it is to take a uniform random variable between 0 and 1. And this, let's assume there is a routine already for you in the computer. And then you just set x mu to be the inverse of the cumulative distribution function evaluated at this uniform random variable. This will be of law mu. Okay, and now I'm setting, if I use the same uniform random variable to also construct a random variable with low nu. Then this introduces a non-trivial coupling between the two random variables. And this I will call monotone coupling because, as you can see, they will move together monotonically. Like when on a realization, when x nu is larger, the x nu will also be larger. Okay? So there is some coupling like this, and yes. So that's one way to define this this coupling. And concretely, if we think of two measures as being sums of Diracs with the same masses for each Dirac, so let's say mu looks like this, and nu has the same weights but at different positions, with the QKs being ordered. Then this straight line that I was describing, this law of 1 minus t x nu plus t, so the transport movement, let's say, will be given by what we think, which is just to slide each Dirac from one position to the other position. Okay, and the optimal coupling is that so that whenever one variable is equal to qk, the other is equal to qk prime. Okay, and I say all this just to justify a little bit more this notion of derivative with respect to a measure that we talked about last time. So if so let's say formally for a smooth function G on the space of measures, we would like to define this derivative d mu G of mu x, so x in the support of mu. So in general, I think about trying to capture what happens when I move these Diracs. But for a general measure, I'm going to record what happens when I move some point on the support of the measure. Okay, so this x is here to record where I'm doing the movement. And we would want so that G of, if I do a first order expansion of G near a measure mu, I will have a formula of this sort. So d mu G of mu plus something of lower order. Because this is as nu tends to mu, in the sense that this quantity goes to 0. Okay, so if you are familiar with this quantity here is the Wasserstein distance between the two measures. And I don't actually want to emphasize this very much. It's just to give you some context into why I like this notation with d mu of some functional. So let's say concretely, when mu is a sum of Diracs as above, so you write it, sum of zeta k plus 1 minus zeta k delta qk. You can check that this amounts to defining Okay, so x is qk now. This derivative the way I said last time. EQKJ. Oh, okay, so I mean it's a slightly informal notation, but when I write this, I think that we think of G as a function of the QKs, and we differentiate with respect to one of these variables. And this is a new notation, which let's say by definition is what is on the right-hand side. Okay, but I claim without further explanation that this notation is consistent with this first order expansion. Okay, and so, this is okay, just some motivational talk to justify a notation. So it's not very crucial. And perhaps the one thing to remember is that you can always think that all the measures we talk about are sums of Diracs. And I want to recall what happens when we move the positions of the Diracs. And if you think of the function as a function of all of these parameters, the position of the Diracs, then the derivative should be a gradient with many, many coordinates. And instead of writing this as a very high dimensional vector, I just index it by this argument here, okay? So I just write qk to say which Dirac we are moving around. All right, so that was just a small conversation. Yeah, so I just, okay, so I claim that this is what I want, but yeah, you can object to it. Okay, so. So in fact, yeah, so there's a question in the chat, but so it's a little bit more subtle because the x is in the support of mu, so it's not the definition, the space over which this thing is defined is not a product space, right? Because the space in which the second variable belongs depends on what the first variable is. Does that make sense? So it's just yeah. If you want, yeah, it's a function in L2 of mu for each mu. All right. Yes. So that was just some aside. This is the end of the aside. To justify this notation, which is closing this aside, and now I want to recap what we have done last time. So from last time. Okay, so the first thing is that we define this Poisson-Dirichlet cascade. You remember it's this structure which iterates these Poisson point processes with polynomial weights with the exponent that varies according to the depth in the tree. And then we multiply all these weights to get some numbers on the leaves. And then we normalize this whole calculation so that the numbers on the leaves become a probability measure, so that they sum to 1. This is the probability, the Poisson-Dirichlet cascade. And then we defined our enriched free energy using this notion. So Fn of T mu, this is -1/n. I will rewrite the definition. So there is our, the Hamiltonian that the energy function that we want to study. And then there was this, maybe I used some shorthand notation last time, but yesterday, but now maybe it's more convenient to rewrite it explicitly. So it's this times this Gaussian dot sigma. And then, okay, there's always this compensating term at the end. That's it. And then there's I should add here a V alpha dp n of sigma. Okay, so now you should really think that instead of having only sigma as the variable of integration, we have sigma and alpha. Okay? It's a bit unfortunate that I have to use two different symbols, one integral and one sum. But really you should just think it's just one integral over sigma and alpha. I could set up some notation so that this is true. And okay, and then the Fn bar is the expectation of Fn as usual. And we saw that we saw two things. So first, well, something that we already saw a long time ago, which is that when we differentiate with respect to t, so this is for the SK model. Okay, there's only one type. The derivative is the square of the overlap with respect to t. And now when we do this differentiation with respect to these points in these QKs, like the position of the Diracs in the measure, what we have found is that, so maybe I write, so it's normally fn bar is a function of t and mu, but then with this new notation with the derivative with respect to mu, I have to also indicate the position of the Dirac that I'm moving around. So it's, let's say, QK. And this we found is the conditional expectation of the sigma overlap given that the alpha overlap is equal to k. Okay, and I claim that this is progress compared with the situation in which we had only access to the expectation of the sigma overlap. And the reason is that, so in our first naive attempt, the error term was the variance of the overlap. And now I claim that we can make it be the conditional variance given the alpha overlap. And so what does it mean, the conditional variance? So let me write it down. I mean that I claim that we should be able to get our error term be of this form. So it's going to be this minus the conditional expectation given the alpha overlap squared. Okay, so maybe I'm going to actually do the argument a little bit from the end backwards, because I'm going to start from this, which I claim can be made to be our error term, and I'm going to try to take a few steps back so that we recover the derivative in t and the derivative in mu. Okay, so this is the error term we want, and so just like with the normal variance, if I expand this square, I get sigma the sigma prime over n squared minus the expectation of the squared expectation. Okay, the first term is the t derivative. And now maybe for the second term, I'm going to introduce some indicator functions that alpha wedge alpha prime is equal to k and sum over k, so that I can match with the previous formula. So let's say minus sum over k of this multiplied by the conditional expectation. Sorry, now there's no more. Like this. Okay, so it's just a decomposition into all possible events. There's a bit of a lag in the display, it seems. Okay. It's coming. Oops, no, it's not coming. All right, sorry about this. Let me change my setting a little bit. All right. So yes, I'm going to be back on very soon. That should do. I thought it should do. Yes. Okay, do you see the screen? Cool. Yeah, so I did my decomposition into independent events. And now, yes, the point is that it was meant so that we recognize this derivative in mu. Okay, so it's showing up here. And remember, or maybe not, but this we have computed, this is a zeta k plus 1 minus zeta k. So let me rewrite all this. This is equal to partial t fn bar. Oops, this is an n. Minus sum over k of zeta k plus 1 minus zeta k times d mu fn bar t mu qk squared, right? And so here we see that this sum, I can think of it as being actually some integration of this function d mu of, and this is the variable. This is, I can think of it as being a dot against the measure mu. You remember the measure mu has Diracs at the qk's, and the weights are precisely these guys. Okay, so let me write this. So more compactly, I can write this as partial t fn bar minus integral of d mu, and I'm going to be using a little bit implicit notation. I'm going to just write it like this. Yeah, I'm kind of dropping the argument. Okay, but we understand that this means d mu fn bar of t mu x, d mu of x. Okay, maybe I'm going to write it in the margin. Okay, this is, I should write integral of d mu of fn t mu x squared d mu of x. Does that make sense? So x is the variable of integration, and we integrate against the measure mu. Okay, so to summarize, what we get here is that, so summarizing this calculation, what we have found is that this quantity is equal to the conditional variance that we started with. This is a wedge. Okay, so you remember in our naive attempt, we did something similar, and on the right side, we had the variance of the sigma overlap, and now we have this conditional variance. And so now the claim is that, and this is the difficult part of the proof, but the claim is that if our Poisson-Dirichlet cascade, if our tree structure is sufficiently rich, and sufficiently rich means that there are sufficiently many layers which are with the zetas that don't increase, that span the whole interval 0, 1 without leaving too much gaps, then, and since the true Gibbs measure kind of wants to be organized in this structure along a similar structure anyway, it will be essentially costless from the point of view of the sigmas to align itself with the structure of the cascade. And so, in fact, with high probability, the sigma overlap and the alpha overlaps will be synchronized. And what do I mean by synchronized? I mean that up to a small error, if I reveal to you the alpha overlap, then you will be able to infer the sigma overlap. Yeah, and this is a much more refined statement than saying that the sigma overlap has small fluctuations. And in fact, this statement is true in some sense. Okay, at least for most parameters, something like this. And so, yes, this is what I hope to explain. And but the argument is I will not be able to explain completely. Yes, but first I'm going to continue making a few more comments and then try to see what shows up in place of this relation when we speak about the bipartite model. Yes, so I'm going to make a few comments first. So for now, yeah, this notation with the measure, it seems just maybe a convenient notation, but perhaps one thing I would like to point out is that this function fn bar is really a continuous function of the measure. So so let's say we have so if I look at the difference between this free energy computed at two different measures, this is controlled by this quantity on the right side, which for those who know is actually the Wasserstein W1 distance. In any case, it's some natural notion of distance in the space of probability measures. Okay, so maybe I'll give a sketch of proof of this. Which perhaps is useful so that we get more familiar with this measure way of thinking about this variable. So I'm going to do it assuming that I can represent these two measures in the following form. Well, as the form I was assuming already many times. So if you think carefully, you realize that in some sense I can always, if mu and nu are sums of Diracs, then you can always represent them in this form. Because you just make sure that all the levels are filled sufficiently finely, and but when you do this, you may have repetitions in the Q case, and in the definition of Fn bar I gave, I assume that they were not repeating. So also for the so here I'm assuming that they have this form without repetitions in the zetas and Q. So that's why it's actually only a sketch of proof and not a full proof. I will have to justify that even if there are repetitions in these representations, the way we computed the Fn bar is still valid. The Wasserstein distances. So there's a question in the chat about Wasserstein distances. So they can be defined for arbitrary exponents. So this is the W1 distance, like the one based on L1, and you can also define it based on L2. So yeah, all are fine. Okay. There's different distances, but okay. So in this case, if we suppose that mu and nu have this form, then and I don't write, but the QKs are ordered, the QK primes are ordered. then this quantity, this Wasserstein distance, indeed, can be written explicitly as the sum of the zeta k plus 1 minus zeta k times qk minus qk prime. Okay, because you remember the coupling makes it so that whenever x mu is equal to qk, the other one is equal to qk prime. Okay, so what I need to show here really is that this quantity is bounded by this sum. And remember that this derivative with respect to qk of fn bar, we have found it to be the expectation of indicator function of alpha wedge alpha prime equals k times the sigma overlap. So the absolute value of this guy is bounded by, so you remember the sigmas have norm at most square root of n also. So in absolute value, this term is bounded by 1. So what remains is just the expectation of this indicator function. And this we saw is equal to zeta k plus 1 minus zeta k. Okay, so that's in fact the end of the proof, because in order to move from mu to nu, you're going to just move one variable one at a time. Q1 you move to q prime 1, and there you pay the derivative, which is zeta 2 minus zeta 1 times the difference between q1 and q prime 1, and you go on, and all you do is exactly this. Okay, so that's the end of the proof. Yeah, with the slide sheet that I have to explain that even if there are redundancies in the representations, what I have done is still fine. So we are good. So in fact, you see that yeah, so far I was writing fn bar of mu, but I had only defined mu for measures which are sums of Dirac's. But in fact, you see that using this result, you can extend it to really any measure with, let's say, a finite first moment, because by continuity, you can do it. And yeah, hopefully it also gives some more credence to the idea that, thinking of these derivatives as using this, let's say, derivative with respect to the measure notion makes sort of sense. Okay, and yeah, before I move to the bipartite thing, I want to make one more comment, which is, so now what I would like to say is that when n goes to infinity, the partial differential equation that we need to talk about is exactly this, but except with the right-hand side being 0 instead of this error term. And in order to make full sense of this consideration, I also need to talk about what happens when, for the initial condition, what happens when we set t equals 0. And yeah, so let me perhaps display one more time the formula. So this is the formula for the free energy. And when we set t equals 0, so these terms here disappear. And what remains is of product form. You see that it's it's a sum of terms which only talk about each one. One is going to talk about sigma 1, the other about sigma 2, and then sigma 3, etc. But there is no interaction between the sigmas in what is left. And this is the structure that is key to doing the same arguments as we have done for the Curie-Weiss model or for statistical inference. Okay, so in fact, we can still justify that when we say t equals 0, this object does not depend on n. Okay, so let me write this down. So we have notice also note. One can show fn bar 0 dot does not depend on n. And in fact, the argument is, I'm not going to give it entirely, and it's a bit more involved than those we have seen for the other cases. But the key ingredient to justify this, and in fact also to give a more explicit procedure to actually compute this object, is this observation we have seen about Poisson-Dirichlet cascades that. So if, let's say, if Vn is let's say just a Poisson-Dirichlet process with parameter zeta, then we have this expectation log sum of Vn xn, where xn are independent IID random variables, independent of the V. This is equal to 1 over zeta log of expectation of x1. Okay, so using this thing, you can peel off progressively all these layers that we have built into the Poisson-Dirichlet cascade, and recursively compute this fn bar of 0 dot. Okay, so it's not a super simple calculation, but it's you're just iteratively doing operations of this sort, where zeta is zeta k, and then zeta k minus 1, and then zeta k minus 2, etc., up until the moment when you have unpeeled everything. Okay, so in some sense, the initial condition is that can be sorted out. So let's say denote psi fn bar of f1 bar of 0 dot. And perhaps, yeah, I'm going to clarify this question in the chat just now. So, yeah, perhaps I remember that someone was at some point was asking about why we are asking questions about the assumption about this measure Pn, that here for simplicity, I assume it's of product form. It's a tensor product of a fixed measure. But in fact, all what you need is that this fn bar of 0 dot converges to something. Okay, so when the measure is product, it's clear because it actually doesn't depend on n. But if, for instance, you're doing a spherical model, then you can show that this converges, and this is enough for what I'm going to say next. Yes, and now, so let me try to address the question in the chat and also summarize what we would like to say for the SK model. So summarizing again. We would like to say that as n goes to infinity, this fn bar converges to f. So it's going to be a function taking for arguments a non-negative number, t. So maybe I'm going to write the variables. So non-negative t and a probability measure on R plus, taking values in R, which is supposed to solve the equation that we have discovered, partial t f minus integral of d mu f squared d mu equals 0. So this is on r plus cross. And okay, so I'm going to say it's on P2, like those measures with finite second moment. But, you need some moment condition. P1 would also be fine. Let's say P2 for definite. And then the initial condition is this function we just talked about. Okay, does that answer the question in the chat? Yes, and now so this is what we would like to do, but fortunately, people have thought about spin glasses before we talked about Hamilton-Jacobi equations. So in fact, we can answer positively this question because we can bridge it to previous work on the Parser formula. Okay, there's a question in the chat, but I'm not sure if I understand it. So maybe I will leave it to the break, which we'll take shortly. And maybe, yeah, if in the meantime, maybe if you can clarify your question, that would be awesome. Yeah, so now what I want to do just before the break is bridge this, which I phrase as a question, into an affirmative answer, because I'm going to connect this with the standard Parser formula. Okay, so notice that in this equation, this thing is a convex function of the derivative of f. Okay, just because it's you're just taking a square and you're integrating, and therefore we know our Hopf-Flachs formula. So we should expect that there is a variational formula for this equation. So maybe it's a little bit more scary because it's in the space of probability measures, but we're not afraid. So plausibly, there is a Hopf-Flachs formula for this solution. And so what does it look like? It says that f of t mu is the supremum over nu. Again, I'm doing this. So P2 is with a finite second moment. No, again, not crucial. Let's just not pay too much attention to this part. Minus, and then I would have to justify it more carefully, but I claim that this is the right way to write the Hopf-Flachs formula. It looks like this. Okay, and so I have not defined properly even what is in what sense does this equation hold? And I should do that. And the point of me presenting this Lipschitz estimate for the free energy is so that you are convinced of the fact that if we want, without loss of generality, we can always assume that we only deal with measures which are the finite sum of Diracs. Okay, we just take them sufficiently fine, but we can just pretend that every measure is just a finite, just very large sum of Diracs, and if there's enough Diracs, we do extremely well in terms of our approximation. And so instead of writing this infinite dimensional equation, you can write a finite dimensional approximation. And once you write this, you're in safe territory. You can apply the Hopf-Flachs formula that we saw. And you can see that as you refine these Diracs more and more, in the limit, what you see is this. Okay, so I'm not going to do this calculation, but it's nothing very fancy. It's not complicated. Maybe this notation, because you're not yet super familiar with it, it looks a bit intimidating. But you should think, if the measure is just a sum of Diracs, which are all of the same size, I told you that you should think of this function d mu of f as just a big gradient, and then we are just taking the square norm of this big gradient. Okay, so this equation, which looks intimidating, its finite dimensional approximations are just partial TF minus grad f norm squared equals 0. And we figure out what is the Hopflax formula for this. And I claim this is what is on display. And so this result of Mourrat and Panchenko states that at least when we restrict to the case when mu equals 0, this formula is valid. I mean delta 0. So theorem, which really is due to I mean, it's borrowing from the hard work of Mourrat and Panchenko. But okay, to prove exactly this in the setting I'm displaying now, it was noticed in some paper I wrote, and so the claim is that, but this paper is a very is a much more modest contribution, let's say. At least from a technical point of view, that this limit is f of t mu as defined above. Oh yeah, no, sorry. So this, yeah. So in the paper, so this was really fully justified. Actually, later in a paper of Panchenko and myself. Okay, I mean, it's not too crucial. Okay. Anyway, so here, it's nice. It's reassuring. I have not. It's reassuring because it means that I have not like annoyed you about this approach uselessly, because it says that indeed it brings us on the right track. It actually identifies the right object. But the way this thing is proved is not actually using the partial differential equation interpretation. Okay, so it borrows from a previous work that was based on this variational formula, which up to a change of Albers is the Parser formula. So it's a nice let's say sanity check for this thing. But so after the break, I'm going to discuss the bipartite case, and there we will have no variational representation for the limit for energy, and so the traditional approach cannot even be phrased in some sense. And the PD approach, so far, I have only partial results, which I'm going to explain. Okay, so are there questions on what I try to describe here? Yeah, there's a question in the chat, but I am still a bit uncertain about what it means. I guess you mean that I want to use this contour. Do you mean the duality in optimal transport, or this contour-Wish duality thing? Or? Okay, uncertain. So yes, which is this contour-Wish? Yeah, so I mean, at some point you need to know something about your function. So you need to open your. So you mean to prove this Lipschitz estimate for the free energy, right? So at some point it needs to take into consideration what this function is. So you need to compute something that relates to this function. I mean, the proof I gave is not so bad, right? You just compute the derivative and kind of works. Yeah, so I have the impression I'm not quite understanding what you have in mind. Okay, I think. Yeah, okay, yeah, maybe. I'm not sure. Let's just do that. Yeah, that's right. So there's another question in the chat, which is about whether the measure can be any measure, but still having unique solutions. You should really think that this measure is some extension of this H parameter we had before. And we were like, if I kind of read your question and replace the measure mu by the parameter H, you see, you would not be so surprised. You would not say, oh, but the parameter H can be any parameter on the real line, but the solution is unique. It's like, yes, right? And here it's a bit the same. The measure can be. Does it make sense? Like we're describing a function of the measure, and we're saying that the relations like. Okay, it seems to make sense for you, so good. I'm not going to confuse myself more. Okay, so maybe as we. Yeah, so perhaps it's related to the comment I wanted to add, because I think I was not very clear on this point. Thanks for this question. So, okay, fine. We have the limit of this. How does it relate to the original question we were asking? Like down the road, we want the limit free energy of the SK model. And okay, you have enriched your free energy and confused ourselves, but and confused us. But where is our object? So the original object is recovered when we set the measure mu to be the Dirac at 0. So yeah, this is not super obvious, but let me display one more time this free energy. Yeah, so perhaps one first thing one can observe is if you choose mu equals the Dirac at h, in fact, this recovers our guess with the random magnetic field. So because there will be only one term here, and it will be square root of 2h times z times sigma. Yeah, I'm really not writing very well here. And so this is our stuff with the random magnetic field. And now if you set h equals 0, then in fact this term disappears. And the last bit also would be, okay, so let me, that's not what I want to do. Yeah, so if you set mu equals delta h, then this whole thing becomes square root of 2h z dot sigma minus nh. And now if you set h equals 0, everything disappears, and you're left with the stuff you really care about. So the stuff we really care about is obtained by setting mu equals the Dirac at 0. Maybe I could have left it. And so really to make the connection with the free energy we care about. Oops. And so the Parser formula. So up to a change of variables, which is not very consequential. Formula is this Hopflax formula here. So this guy with mu equals delta 0. And perhaps it's also reassuring a little bit because if you actually have come across the Parser formula, you've probably noticed that there is no talk about monotone couplings between random variables and blah blah blah. So what's going on? What is going on is that when you set mu equals Dirac at 0, you know, the variable x mu is just 0. It's deterministic. So there's no subtle coupling to do. And this whole thing is just you're integrating this x nu guy squared. So this is just integral of r squared d nu. Does that make sense? So this is just a side comment. So for this choice on mu, when we write expectation of x nu minus x mu squared. So I claim that this guy is 0, and then x nu is just some random variable with low nu. So this is, I could also write it as integral of okay, my r's are funky, so maybe u squared b nu of u. Okay, and so we have some integral against nu, and okay, yeah, then okay, we have to do some extra variable maybe, but at least it starts to look a little bit more familiar to the way the Parser formula is actually written. So does it make sense so far? Like so to sum up, with this more refined free energy, we have a guess for what the limit free energy should do, and I have not explained how we could approach proving it, but at least we can verify that what those guys have found by other methods matches this prediction. And now my goal is to explain how to extend this to the bipartite model. Okay, so I want to state a conjecture which is consistent with what we just said for the SK model in the case of the bipartite model. So now, so there's a question in the chat. So indeed, if you want to think about the model with some, if you want to figure out the free energy of the model with the magnetic field square root of 2h z dot sigma, then you have it from the same result by setting mu equals delta h. Does that answer the question? And if you would rather have h be a deterministic field, as in Travis, like h sum of sigma I type of thing, then this you can insert into the probability measure. So this is also taken care of. So it will only change the definition of the initial condition. All right, so what do we do for the bipartite case? In fact, we do exactly the same thing, except we allow ourselves to influence separately the first component of the sigma and the second component. So instead of having one of these magnetic fields with this hierarchical structure, we'll have two of them. So yeah, so we want to act to have random magnetic fields that act on each component of our configuration, which is, you remember, it has two parts. Each, there's just, for convenience, we have said each is a vector in Rn. Okay, so again, if you want to make one be a bit longer than the other, maybe 2n and one 3n, that's also fine. But, so therefore, in this case, we're going to, I'm just going to add some indices 1 and 2 everywhere, in the Z Gaussians that we insert and in the measures, and then we're going to define the free energy and see what happens. So there are these Gaussians indexed by the tree. Now there are, for each node, I have two of these Gaussians. Okay, and so we have families of parameters, Q1k and Q2k as before. So I'm going to use the letter A to denote an index, which is either 1 or 2. So there was this Z, I noted them ZQ of alpha last time, but I'm going to keep implicit that they depend on Q. I'm just going to record if it's supposed to go with the sigma 1 or with the sigma 2. Okay, so it's Z1 and Z2. So ZA in this notation. It's sum for K from 0 to capital K of 2Q. Let's say, if A is 1, it is Q1K minus 2Q1K minus 1 square root Z1 alpha up to level K. Okay, so exactly the same definition as before, except I inserted these A's everywhere. And now we can define our enriched free energy. So maybe I'll just write Fn bar. Okay, so I should say mu1, so mu A is sum of, zeta k plus 1 minus zeta k times delta q ak. So I assume that the zetas are common to everyone. Okay, and similarly, the Poisson Dirichlet cascade will not be duplicated, because ultimately I want that everybody synchronizes together according to these zeta levels. So there's only one probability cascade. It's only the position of the Diracs which are allowed to vary freely. Okay, and now if I write mu, I mean the pair mu1, mu2. Okay, so what is our free energy? -1/n log. So, okay, as usual, I have to write integral sum now. So it's on the leaves of the tree of the exponential of square root of 2t hn of sigma. So now it's, I use the same notation, but I mean that this now is the bipartite guy. Yeah? And then I add these magnetic fields. So plus z1 of alpha dot sigma 1. Okay, and there's always this compensating term q1k plus z2 of alpha dot sigma 2 minus nq2k v alpha dpn sigma. Okay, so it's really, oh, and I put a bar, so I should put expectation here. It's really exactly in the same spirit as before, except we have duplicated these random fields. And all right, so now I can still define my Gibbs measure, which will be with respect to random variables sigma and alpha as before. And I can compute the derivatives of fn bar. And well, when I compute the derivative in t, nothing changes with respect to what we had done with our initial guess. So it's still going to be this product of the overlaps. So you may or may not remember, but what shows up is this product of overlaps when we do this derivative. And when we differentiate with respect to the positions of the Diracs, so let's say d mu a of fn bar. So a is 1 or 2, okay, at t mu q ak. We will find again this conditional expectation of the sigma overlap given the alpha overlap, except since we, in the definition of the exponential, since z1 is only acting on sigma 1, the sigma overlap that we will see is the sigma 1 overlap. Okay, so we will see sigma 1 dot sigma 1 prime divided by n conditionally on alpha wedge alpha prime equals k. And so this time our goal is that, so maybe I'll do again the calculation in the reverse order. Oh yes, thanks for the comment in the chat. I like so much to say that A is 1 that no, I write 1. So yeah, this is sigma A indeed. So yeah, maybe I'm going to proceed as before, starting from the error term I'm shooting for. So when we were doing our naive guess, our error term was this sort of covariance between the sigma 1 overlap and the sigma 2 overlap. And now I'm going to hope for a conditional covariance. So something like this, sigma 1 dot sigma 1 prime divided by n minus conditional expectation given this thing, and then multiplied by the same thing with the 2's. Okay, and if I expand, so if I expand again, I will see, the first term will be the product of the overlaps. And the second term will be the product of these conditional expectations. The first term is the t derivative. And the second term, we do as before, we write this sum over k of the indicator function at alpha wedge alpha prime is equal to k. And then what we see on the right is these derivatives. Maybe I'm going to directly write the derivatives. D mu 1 fn bar of t mu q1 k d mu 2 fn bar of t mu q2 k. Okay, and again, this is zeta k plus 1 minus zeta k. So here the integration should be, so there are two slots if you want. There's one slot here that is varying and one slot here. So I should think I'm integrating against these two variables, and the measure that is relevant for doing this integration is the measure which is actually the monotone coupling between these two things. So let's say defining or denoting by mu hat this measure, so zeta k plus 1 minus zeta k delta of q1k q2k. This is the law of x mu 1 x mu 2. What we get is that, so let me summarize this computation above, dt fn bar minus the product of these derivatives. And again, I'm suppressing the arguments for clarity, integrated against this coupled measure is equal to this, let's say, conditional covariance, sigma 1 sigma 1 prime minus the mean multiplied by the same thing with the sigma 2. And so here, just as in our previous conversation, we see that if we knew that this alpha overlap reveals the sigma overlap, if we knew that the conditional variance of the sigmas given the alphas is small, we would be in good shape. Okay, so perhaps to make it clearest, I can use that AB is smaller than 1/2 of A squared plus 1/2 of B squared. So I apply this inside the expectation. And what I get is that the absolute value of this left side is bounded by 1/2 of the sum of the variances. Okay, so I write a sum from 1 to 2 to save a bit of space. Okay, and again, in this circumstance as well, if we want to compute this thing at t equals 0, it's the same calculation as for the SK, so this poses no difficulty. So here is a conjecture. So the limit as n goes to infinity of fn bar is a function f. So where f is going to be a function of from r plus taking some non-negative parameter t and a pair of measures with values in r solves the equation that we just discovered, which is the version of the naive equation we talked about early this week, but except with measures around. Okay, so dt f minus the product of the derivatives integrated against this coupling equals 0 on r plus cross this thing. Oh yeah, maybe I should put that they have second moments just to be on the safe side. And with this initial condition, which okay, I have not defined, but I claim is not difficult to compute. Or at least it's the same procedure as for the SK model. And we iteratively integrate this probability cascade using this recursive procedure. Okay, so that's the conjecture. And so far, I don't know how to prove it. So the only thing I can say is that there is a bound between these two things. So this is true. So, okay, there's a question in the chat. So you see that the objects I gave myself are really just two probability measures. I had to describe the behavior of, the way these random magnetic fields are splitting around, and there are two of them. And naturally, I claim that it's kind of natural to index this tree structure in the random magnetic field by a measure. And so I have two of them. So I will have two probability measures on R plus. But perhaps just to kind of go in your direction, when you try to make more general models, maybe with more types, or if the interactions between the types is a bit more complicated, then it's actually perhaps best to think of it as, indeed, as you propose, some measure on R plus squared, but with the constraint that it's monotonically coupled. Like it's coupled. It has this. You could think of this instead of. Okay, it's not a very important command, but you could equally decide that the indexing of this function is by this pair of measures, or it's equally valid to say that I'm going to show you mu hat, this coupling between the two measures, and mu hat is in this space you're describing, but it's not living in this entire space. So the equation will still be defined only for those measures on R plus squared, which are Monotone couplings of two random variables. So okay, I think it's clearer to present it this way, but it's possible to go somewhere in this direction. I hope that makes sense. Okay. Yes, and I can. Okay, so yes, so what are the ingredients when we want to prove this? Well, the core thing is to try to justify that indeed this synchronization thing that I'm talking about happens. And for this, the key ingredient is some result of Panchenko, which shows that quote unquote generically our Gibbs measures will have this tree structure that I drew some time ago, with this decomposition into states. And once you know this, in fact, and this is also work by Panchenko, you can prove that this implies synchronization, because it's not only that the sigmas will have to have this tree structure, but any linear combination of the sigmas and the alphas will have to have this tree structure thing. And if you think carefully about what this means, you can see that it must imply that these things are synchronized. Okay, and so the key thing in this business is hidden in this word generically that I said before I stated these results of Panchenko. And it's very similar to what we encountered in our previous cases with statistical inference or query-wise. When we did query-wise, let's say, our error term was this variance of the magnetization. And it's not difficult to convince oneself that generically this magnetization is concentrated, right? Because, for instance, if we touch so the function was convex, and we have seen that if we can touch it from above by a smooth function, then automatically this will mean that the second derivative is of order 1, and this implies that the magnetization is concentrated, it has small fluctuations. So already for query-wise, we have this fact that at most points at which we look at our problem, the error term, like this thing on the right-hand side, is small. But the problem is that this is not sufficient. This is what we talked about with these Hamilton-Jacobi equations. Even if I tell you, so if we even pass to the limit in this situation, I could tell you our stuff solves the equation almost everywhere. And we've seen when we studied Hamilton-Jacobi equation that knowing that something solves the equation almost everywhere is not sufficient to completely identify the solution. And so we are running against this problem one more time. And so why is it so that one bound is easier than the other? Well, it's like with the previous model we have seen. It's that there is a natural convexity in these functions. So in this case, I put a minus in front. So now it's more like there is some. Okay, it's not really. It's like approximately concave, like it's semi-concave. And because it's semi-concave, if I touch it from below, everywhere I touch it from below, I will have some smoothness information on the function. And so I will know that my error term is small there. And this is enough to conclude that our object is a viscosity super solution, because every time we touch from below, things are fine. But when we touch from above, this is not happening. And in fact, I just said it's approximately concave, it's semi-concave, but our function is not really concave or convex. So we cannot use this selection principle I described before. So in some sense, I believe that this conjecture is plausible because in some sense, we can verify that the equation is satisfied almost everywhere, quote unquote. Okay. Quote unquote, because it's an infinite dimensional space and we have to clarify what this means. But when you look at the finite dimensional approximations, you can make sense of what that means. But moving from the equation you want is satisfied almost everywhere to actually this is really the true solution and we're done is a significant difficulty. And for the two previous classes of models we talked about, we found ways to deal with this problem. But for spin glasses, this remains an open question. All right, so I think it's a good place to stop. I hope you enjoyed it. Personally, it was a great pleasure for me to do this. And if you stayed so for up to here to this, and you're still interested in the topic, please feel free to contact me. I'll be very happy to discuss things. Yeah. So thanks a lot for your attention, and yeah, I hope you liked it. And as usual, I'm happy to take questions.
Thanks very much, JC. Before we go to questions, I think maybe we can all unmute ourselves and give a big round of applause for a great course.